So, I'm Jeff, and today my job is to just walk you through a little bit of what we're doing with artificial intelligence. It's one of the many different applications that our universal storage product can support. And there's been so much going on in this space. It's such a hot market. It's such a hot topic. And there's been so much going on with VAST, both internally in the product team as well as with our customers, that I figured I'd just take some time to walk you through a concept that we're about to introduce to the world that we call Lightspeed. So if you take a step back and you look at the foundational principles that we started the company on, we had a belief. And that belief was that as you think about the organization of data in your average data center, what you typically find is that the largest amounts of data are in the slowest and the most affordable storage systems. And then if you fast forward to 2020, what we see happening is that every single organization in the world is trying to figure out ways to apply both big data and artificial intelligence applications to not only new data sets that are emerging from things like IoT sensors and what have you, but also to their pre-existing data sets. Howard talked, for example, about a sports broadcast customer that we have. They're doing all sorts of things like going in and adding AI to 20 to 100 years of sports video. And so this is a market event that will change the way the world operates. And our objective has always been to democratize flash for all of a customer's data. And that has always been at the service of making it possible to basically usher in a new era of computing and transform the way that people can interact with their data and make sure that all of their data is available at real time for these new types of applications. And so, Renan talked a little bit about this, but earlier this year, I mentioned the Department of Energy. Earlier this year, a lot of our customers have started to kind of digest this idea of building tiered architectures for applications that demand read-heavy random access into very large data sets. And one of the things that we're doing is we're basically traveling the world, cleaning up some of the early bad decisions that were made around architecture when people were building things like tiered environments and taking a little bit of flash and a lot of bit of hard drives and trying to move their data back and forth, either internally to a clustered system or externally between different systems. And what they would find is that as they started to digest the performance deltas between if you have a GPU, for example, that accesses a piece of data on flash versus a piece of data on some mechanical media, the difference in performance can be up to 50x. So our fundamental thesis is that these modern workloads basically render the idea of storage tiering obsolete as people start to apply AI algorithms and big data algorithms to their largest data sets. Now, customers, they have a choice. And up until now, they've had a series of very compromised choices. Choices where customers have always had to decide about speed and complexity and cost. And you could go down one of two routes to build the large, let's call it AI training or AI inference framework. My background is in HPC storage systems, parallel file systems, and that's of course one choice that you can make. You can buy something that's really fast and really scalable, but the complexity requires you to maintain a series of PhDs to go and maintain those systems. On the flip side, you can go down the path of a simple NAS appliance, and a lot of the reference architectures in the AI space, they call out things like just standard scale up or scale out NAS products. Now, these are simple to operate and they're easy for enterprise organizations to deploy, but they come at a cost, and that cost is the performance that you can expect to get from your GPUs. Now, the I/O access pattern of these applications, NVIDIA will guide you, is typically between 100 kilobytes in size to 1 megabyte in size. And this becomes kind of a clear argument, in our opinion, for flash infrastructure, particularly as it's random and completely non-deterministic in terms of where the accesses go. And so if we assume that flash is an imperative for AI, then both of these types of technologies, HPC file systems or scale-out NAS appliances, when they're built from all flash, they are prohibitively expensive. You're talking about products that are upwards of 10 to 20 times what customers pay for hard drives. So they always have in the back of their mind that economic envelope that they can get to if they try to do some weird gyrations. And what we're introducing is a different approach. Our solution for AI is to just get down to first principles and eliminate a lot of the common problems that limit people from being able to scale up their AI initiatives. From a single client perspective, we've addressed a lot of the limitations that customers typically find with scale out NAS, such that you can get the same exact performance that you would otherwise see with the most complex, sophisticated HPC file systems in the world. But at the same time, it's just a NAS. So we have complete simplicity in terms of the delivery model. We've already shown you that the product scales out linearly. So as you have these really large projects where people are building AI supercomputers, the product works just fine. And the key is all of the things that Renan articulated that we've done to reduce cost directly apply to us being able to make flash infrastructure much more affordable for these projects.
Hey, Jeff, a lot of these workloads are, image or time series. I guess time series stuff, market data might be fairly compressible and dedupable, but the image data from, genomics and that sort of stuff, typically not very compressible or dedupable. So the sort of advantages that the solution offers for a more, I'll call it normalized, dedupable or compressible data don't really apply in this environment as much.
If you said the word typical, and if you use typical compression and deduplication, that's absolutely the case. The way to think about what we're doing, Ray, the way I explain it to customers is if you were able to zip up your entire data center into one zip file, that is roughly analogous to the compression that you should expect to get from VAST on a global basis. So Renan talked about fine granularity. Our pattern matching goes down to just 2 bytes. But it's a completely global mechanism that goes all the way across your namespace. And so, your standard JPEG has like a few million different colors in terms of different pixels. And, slight variations in the 2 pictures will definitely create offsets that don't compare super well. But, we're selling systems into movie studios where they're seeing anywhere between 1.5 to 1 to 3 to 1 data reduction. We're selling systems into
3 to 1 in the movie image studio?
Yes. We're selling systems into, but there's a reason, and I'll get back to that in a moment. We're selling systems into life sciences centers where they'll see 2 to 1 on uncompressed TIFFs. So not zipped or not LZ compressed TIFFs. And so it is definitely data dependent, our approach, but where every other system leaves off, that's when we start to pick up the global correlations that no other system could find. Howard earlier showed that we're working with Rubrik. Rubrik's already compressing and deduplicating the data. And after that's done, we find an additional 3 to 1 data reduction. So it doesn't work on encrypted data where you have each piece of data with its own unique keys. But there are a number of different commonalities across different files that you have within an environment. We'll determine those. So if you have different resolutions of a video, for example, or something like that. Another example is that particularly with deep learning, a lot of people take images and they convert them into tiles, and those tiles are stored as uncompressed bitmaps, and those are very compressible as well.
All right, thanks.
So it is not a panacea. I'm not saying it works all the time, but when our solution doesn't deliver any gains, that just means that the other solution also won't give even a fraction of the gains that we would otherwise see. And because everybody's bringing more expensive flash to the market that can't survive for 10 years, that has very thick erasure code overhead, we still win. Okay. Now back to the client access performance.
Just only one more thing. This is the first time you show Infiniband. Do you support Infiniband?
Of course.
Okay, I didn't know that.
So we support Infiniband in 2 different varieties. The internal fabric runs on NVMe over fabrics, and Mellanox takes a lot of credit for bringing a lot of this out to market. You can implement NVMe over fabrics over Rocky v2 or Infiniband native verbs. So in both cases, we support being able to build an NVMe fabric on top of either Ethernet or Infiniband. But we also have brought to market a capability that's in the Linux kernel that's been largely forgotten about or neglected over the past few years, which is NFS over RDMA. And so RDMA was basically added to NFS thanks to Oracle. They did a lot of work on this about 10 years ago. And our conclusion was that we could just use things that were in the kernel as opposed to develop up our own complex piece of software that we'd have to deploy in a customer's compute environment. And the Linux community has moved pretty far along since then to make it even more advantageous to use NFS for all of your high throughput applications. And so we have support for both. If you have an all IB environment, we're not even going to bring switches to the table. If you have a mixed environment, maybe we bring switches, but it's up to the customer in terms of how they want to configure the system. Now, when we started working on the AI problem set, which is that you have these new modern machines, like NVIDIA recently announced a product called the DGX A100. This has 800 or 200 gigabit ports that are connecting to the network, and there are applications that will expect to do I/O across all of those ports. And a lot of the NFS vendors in the marketplace will say, okay, well, you know, NFS isn't designed to go over multiple ports. It's not multi-stream, so just create different mount points and have every one of your GPUs point to a different mount point in the machine. And that works if you're dealing with like containerized environments, but some customers are saying, I'm just running one job in that machine. I don't want to have to federate my job into 8 different parts and have each part figure out how to talk to the namespace. And so we've been working with NVIDIA, and here we've kind of pulled a bunch of stuff out of the kernel and enabled the use of it such that we can deliver game-changing numbers for a NAS experience. The first thing is that we started working with them on a capability called GPU Direct. And in conjunction with RDMA, and NFS supports RDMA, we can now not just DMA a piece of data from a storage server up to the CPU memory of a GPU machine, but rather we can place it directly into the GPU memory. And so that saves a copy of data that goes through the machine. And it also allows us to work around the bandwidth limitations that you'd have with CPU memory. And so GPU Direct is a capability that's been pioneered in NVIDIA systems, and it really allows for 2 things. One is the ability to stream data into machines much faster than has been ever possible, but also to avoid using the CPUs at all for I/O. And that's great because these CPUs are also used as like different parts of the AI pipeline where people are using them for things like data preparation and what have you. Now, we've combined that with the RDMA bits that are in the kernel and another capability that we recently found, which is multipathing. And so if you put all of these together, we realized we had to make some contributions to basically to make it such that a single mount point can be multi-port aware, and we make sure that we're sending data down the right paths in order to make sure that the performance is hardware efficient. And when we got there, we started to work with NVIDIA on benchmarking. And this is a set of performance numbers that they presented a few weeks ago. And so, excuse me. So here, they make a previous generation system called the DGX2 that basically has the capability to do about 100 gigabytes a second of peak theoretical performance. And we started working, we basically scaled up the tests to demonstrate the different capabilities of what's in the kernel and what NVIDIA has developed. So we started with just a single NFS session over TCP. And NFS over TCP is it's single stream. It goes to 1 core within a modern AI computer. And because TCP is limited to about 2.5 gigabytes a second, that's basically all you can stream a single mount point of NFS over TCP into a system. Now, as I mentioned, we have support for RDMA. And if we combine RDMA support with that multipath capability, we can see more than just what a 100 gigabit port can deliver. And so we didn't enable GPU Direct. We just turned on RDMA services with multipathing. We said, let's let her rip. And we pegged that system at around 30 gigabytes a second. And the reason for that is that we were completely limited by the I/O processing requirements of that system with respect to managing data placement into the CPU memory buffers. So we're basically CPU memory bandwidth limited. And then we actually didn't have to do any development on the server side. NVIDIA and VAST just kind of turned on GPU Direct capability within the client. And at that point, we were completely bypassing the CPU memory altogether. And so through that, that presentation that NVIDIA just delivered, what they demonstrated is that the fastest performance that they've seen exhibited with this system is not with a parallel file system, but rather with just a simple NFS mount point and code that's running in that machine. And so this is an instrumental part of kind of liberating the market and liberating the AI movement from complex infrastructure. And the other thing to consider is that when we started working with NVIDIA, they kept asking us, but how do you scale and how do you scale? And we didn't really understand the nature of the question. And it's because we didn't know that they were about to deliver a system that singularly could consume 200 gigabytes a second of bandwidth. And so if you look at some of the leading scale-out NAS appliances in the market, that's the most that they can scale to, which makes their question pretty natural. In our case, we have this embarrassingly parallel linearly scalable architecture that you can build to support terabytes a second of performance. And so disaggregation is the key. You need to make sure that as you add more and more infrastructure, that crosstalk across the infrastructure isn't slowing down any I/O process. And the DAYS architecture that Renan talked about is the way that we get there. So we've yet to find a customer that can deliver to us a performance level that we can't hit. And as you start to think about some of these computers that customers are building, they may have like 140 of these DGX very high-speed computers in one cluster, and that's
Hey Jeff. So in this case, the software is running on these V boxes on the bottom, and the JBOFs are behind it someplace. Is that?
No, these are our JBOFs. These are
the JBOFs. So where's the server software running in the DGX A100 solution?
It doesn't. It's just an NFS client. There's no server software running it. There's no container or anything like that that we would provide in that system. We can in the future, but we decided not to do that to start. It's just an NFS over RDMA client that can do 100 times faster than an NFS over TCP experience.
I guess I'm lost. I thought you had a VAST C node that provided an NFS server to somebody's NFS client. And then behind the C node was these JBOFs that provided the Optane and QLC.
Nope, it's just the data path here is, as you can see it, Ray. Let me find my mouse.
No,
NVIDIA systems are clients. You talk to the servers aggregate requests that come from data that's in the JBOFs.
Where is the NFS server in this environment?
These are our
in that middle layer.
In this middle layer.
Oh, the NVMe fabric.
Yep, they're on the other side of the NVMe fabric.
But they're not being shown.
No, from the bottom up, it's the
these are
the JBOFs.
Yes.
And then the NVMe fabric that connects the JBOFs to the servers, and then the NVIDIA A100s at the top.
I got
these machines here.
Those boxes are running your VAST server code.
Yep. There's 4 machines in 2U. They're just stateless Linux machines that proxy out the namespace.
I thought those were switches. I'm sorry.
Oh, my bad. Okay. So you've got this linear model that can be combined with NFS simplicity. The next dragon that we slay is the one of cost, right? So you have a system architecture here that is way more cost effective than your standard legacy flash system. You've got a system architecture here that's way more affordable than even tiered systems, because the pathology that we're observing is that when a flash product or a flash element in a clustered storage solution isn't the dominant amount of storage within that system, the flash vendors will price that up, expecting to charge a very significant premium for flash. And so our use of QLC, our very thin erasure code overhead, our 10-year longevity, and this new type of data reduction, even if it just kicks in 1.5 to 1 data reduction, means that we've completely de-risked the value proposition for customers, and they can afford flash now for all of their data, not just for just the little working set that they're working within. And we have a customer that is kind of testament to this. NVIDIA's, I think, just about to put out a blog post about this if they haven't already. It's called the Martinos Center. They do biomedical imaging up in partnership with MIT and Harvard. And Martinos was in the market for a few of these A100 systems. They were considering alternatively a hybrid system that was both flash and hard drives. We came in at a price point that was 25% less than that, which ultimately enabled them to buy more GPUs, which is what they're there to do, is compute more than just store.
Hey, Jeff,
and then, yeah.
25% less, is that the effective cost, like your previous slide? I saw $400,000 and I saw the top before you switched over, it said effective cost per gigabyte. Is that based on some calculation of compression, deduplication?
2 to 1.
2 to 1. Thank you.
And the nice thing about that is it gives you a completely consistent experience with respect to the training models that you can build, because now your archive is your scratch space or vice versa. And so the real reason that the market is excited about this is because what you have is kind of like an inflection point happening right now, where you've got customers with all this data and all their different applications that they've been deploying for anywhere between 5 to 30 years. And then you have all these new applications that are creeping in, and people are trying to figure out how they actually operate with this. And there's this term that's evolved in the market, which is called shadow AI. And shadow AI is basically a reflection of the fact that the lines of businesses are saying, hey, I need this new capability in my product or my service. And if the IT team can't satisfy it, I'm going to go build my own AI infrastructure. Now, none of them want to do that. So the second that they make that purchase, they try to saddle it onto the IT team and say, hey, can you support this? And if your storage is so exotic that it's single purpose to these applications, then it's going to be very difficult for these organizations to kind of adopt AI storage infrastructure to support these modern applications. Now, VAST systems are used for everything from VMware to WordPress and all in between. We've got customers that are representing all of the different types of applications and workloads that you would find consuming NFS, SMB, and even to some extent S3 for the better part of the last 20 to 30 years. But the same product and the same technology gives you the best experience for these new modern AI applications, such as TensorFlow or Spark or Parabricks. So if you put it together, it's basically the mechanism that you can use to modernize not your infrastructure, but your data. Because remember, at the core of it, we're also a completely multi-protocol system that allows you to write data via any NAS protocol, read it via S3, or vice versa. And that's why we call it universal storage, because it's a product that you can use for pretty much anything. Now, Howard covered in broad strokes what we're talking about in terms of our performance, but we are about to make some pretty significant announcements around a future update to the product that we call Lightspeed. You can imagine a dramatic reduction in the footprint of the system, a dramatic increase in the performance of the system, and I don't want to make any of the journalists mad by telling you everything today, so I'm just going to tease you with that and say keep an eye out over the next 2 weeks, and we'll be talking about Lightspeed. Why do we call it Lightspeed? Just as a preview, it's because you get all the performance of the fastest storage systems that you can buy in the world, but at the same time, there is no overhead associated with deploying and operating it, and that's why we call it Light. And so stay tuned for that. We'll be talking about it over the next couple of weeks, and I'm guessing that we'll see you again in another 18 months.
Howard, Jeff, so what's your partner network today? Are you partner centric, or are you guys going direct still, or I mean,
100% partner, always have been.
Okay, so
yeah, so we built a very lean organization. One of the things that Renan talked about is the fact that we'll achieve break even before any of the kind of leading storage companies have done. And one of the ways that we do that is that we're reliant very heavily on our partner community to kind of offset the cost of sale. And so we have more than 50 partners across 5 continents right now that are transacting systems, and our average selling price is over $1 million. So as a result, you know, every time a partner kicks in a deal, it's a very meaningful contribution to our story. So I'm Jeff, Jeff Denworth. I run products and marketing for VAST Data. It's one of my first times in the office since the beginning of the coronavirus. And right before we left, we bought a bunch of toys. So I'm going to pull those out because we get to do some fun stuff. What? No way. So here, I'm going to take my own Ellen picture with the delegates. Wait, hold on. I can do it like this. And then you've got one of these things. So yeah, we get to play with all this stuff that we bought, and we thought we were going to go to all these conferences and have a lot of fun. And turns out we didn't get to do any of it. So